Hello everybody, we will continue our lecture series on this optimal control guidance and estimation course. So far we have talked about lot of lectures on so called LQR theory, that linear quadratic regulator theory, and various extensions on that and everything we discussed. Now we will more slowly start moving on to the nonlinear systems and all. So these are the two techniques that has appeared not very far off, about 10-15 years back, all these development happened, and then we will see how these are applicable to the nonlinear systems actually. So one is called SDRE method, state dependent Riccati equation method. The other one is also called theta D design, and both of that are applicable to a class of nonlinear systems with same regulator in mind actually. So let us see that. And the topics in this particular lecture is first we will give a good overview, fairly good overview of state dependent Riccati equation design. Then we will move on to theta D design. On the way, we will also talk some sort of benchmark example problems to make the ideas clear actually. So, start with SDRE design. It has become quite popular, and then because it is a simplest form of nonlinear control design, nonlinear optimal control design that I can think about. The whole idea here is you somehow kind of repeatedly use the LQR solution that we know actually. So, let us see how things proceed and things like that. It will be very apparent and very clear very quickly actually. So, these are some of the references that I have used and I will be using, and some of these things you can think of using that as well actually. And of late, I think if you really want one reference, then the last one is something I will recommend. This is something like a review paper. It appeared in a annual reviews of control, which is actually a review journal about 2010, and then a little bit prior to that, the same author has presented this, and it is available in the conference proceeding also. This is 17th IFAC World Congress. He has presented the same paper, but the journal version happens to be little more complete and little more extensive and all that actually. However, the conference version should be available freely. All that you have to do is probably register yourself in the IFAC paper saved online actually. Then you can download it actually that way. Anyway, but the whole idea started with some time back it was there when the people were talking about LQR and all that. However, J.R. Cloutier, who happens to be a scientist at Eglin Air Force Base in US, took it to a very high level. In other words, he started all this deep research on this method, and then a lot of good nice theoretical results also he proposed. So, in a way the lot of credit goes to him and his co-workers actually. Okay. So, with that let us see what is SDRE design, its usage and all that actually. So, before talking about SDRE design, the utility part of it largely falls down into these categories actually. First thing is nonlinear suboptimal control design, and remember we are not talking about an optimal design per se, because the system dynamics will you will understand as we go along. The system dynamics is not used as a nonlinear system. It is somewhat approximated as a linear looking dynamics and all that actually. So, that brings in the issue of suboptimality, and also we will see theoretically why it is suboptimal actually. So, it is used first thing as a regulator design, and then something like a servo design or tracking problem, and you can also use it for H2, H infinite design, things like that, and also you can use it as something like a nonlinear suboptimal or observer design, like like filter designs also basically. So, what happens here is whenever you see a Riccati equation, in other words all these things we will talk about some sort of a Riccati equation. So, whenever you see a Riccati equation based design, then the state dependent Riccati equation technique can be brought in actually. So, that is where the utility is fairly wide. Now, talking to the this SDRE design problem statement and all that, this first thing is what you are looking for is a performance index in quadratic form. Okay. So, very close to what we know in LQR design, especially infinite time LQR problems, okay, TF goes to infinity. So, but in addition we will also see that this Q and R can be function of states also, it need not be constant matrices, okay, or need not be only a priori fixed constant numbers and then matrices and all that actually. You can have a design based on Q, which Q itself can be a function of x, and similarly R itself also can be a function of x, and these are additional freedoms in this design basically. Okay. But more important is you should have a system dynamics in this form, which is called as control affine form or linear in the control form, typically known as. So, you have all the nonlinearities in the f of x and b of x matrices. F is a vector and b is a matrix, but u, which is control variable, appears linearly actually. That is a key requirement. But in addition to this what you see here, this f of x and b of x and these two things will need to satisfy several other conditions as well. The very first thing is this f of x and b of x as well as q of x and r of x, okay, they should belong to class C k, where k should be at least 1. Okay. That means, when you talk about class C 0, it is continuous functions. Class C 1 is something like derivative is continuous and things like that actually. Okay. The first order derivative is continuous. Class C 2, when k equal to 2, is the second order derivatives are continuous, things like that actually. So, what it demands is at least first order smoothness of all these functions actually, functions and matrices. Okay. In addition to that, you must also have f of 0 equal to 0. Okay. That remember, when the whole idea here is to minimize the deviation, minimize the take x to 0 basically, that is the whole idea here. And once x goes to 0, then x dot should also go to 0, because x goes to 0 asymptotically, then x dot should also go to 0. And in that situation, what happens is u should also go to 0. Okay. So, if this one x dot goes to 0, okay, and u goes to 0 and f of x is non-zero, then there is a incompatibility issue. In other words, when, okay, let me explain that a little better probably. When x goes to 0, okay, your u should go to 0. Okay. Then what happens if this goes to 0, okay, u goes to 0, and this is non-zero, let us say, okay, then this will not be this will also be non-zero. Okay. That is the problem actually. But if it is, if this also goes to 0, one second. Okay, so if this also goes to 0, then this also goes to 0. That means there is a compatibility problem actually. The compatibility is maintained sort of thing actually. So, why you want that? Because once you go to the steady state, you do not want to deviate from the steady state actually. So, that is the whole reason why under steady state control should go to 0, and once control goes to 0, then the state derivative should also remain at 0 actually. Okay, so, that is the reason why we want that actually. Alright, so the next condition is b of x should be non-zero for all x actually, and that is directly visible, because if b of x happens to be 0, then no control design will work. Actually, it leads to the loss of controllability actually. So, if your b of x has to be non-zero for all x actually. Then in addition to that, J has to be globally convex, okay, because we are all talking about Riccati based design, derivative based approach and things like that. So, J has to be a convex function actually. And the key technique here is the f of x has to be decomposed into a of x into x, okay, that is called state dependent coefficient form. And remember, we are not talking about Taylor series linearization and all that actually. We just see the function and just try to extract or just simply algebraically write it this way. So, if you write it that way, there are various options one can write, it is not unique of course. And whatever a of x you select, then this a of x and b of x should be pointwise stabilizable. That means, if you put a value, if you put a value for x, then the a and this two becomes some sort of an matrix, or some a matrix and b matrix will have numbers now, and at every value of x that you put, then this a b pair should be stabilizable. So, these are the requirements before proceeding further. In summary, what it means is you should have a control affine system, and you should aim for something like a quadratic cost function. In other words, the aim is to design a regulator where x should go to 0 actually. Then the conditions required are like this: all the things f of x, b of x, u of x and r of x has to be at least class C k, f of 0 has to be 0, b of x has to be non-zero for all x, and then the j has to be convex, and when you write f of x like this, a of x into x, then a of x and b of x has to be pointwise stabilizable. So, under these 5 broad conditions, let us see how to proceed. The idea is extremely simple. You have a j already quadratic looking form. Okay, it is not strictly quadratic, because once you put q of x and r of x, then at least this part is not really quadratic, but assume that q of x is just a number after substituting some values of x, then it happens to be something like a quadratic cos function. And you are also writing f of x here as a of x times x. So, once we write it that way, then x dot is nothing but a of x times x plus b of x times u basically. So, what it happens? It is like a something like a linear looking form, or I mean it is known as something called SDC form, state dependent coefficient form. So, once you see this, and just imagine for a second that we know the information about state. So, if you once you substitute it, I mean once you know the value and substitute it here, then q, r, a and v takes the form of some numbers, and hence you can interpret that as some sort of a standard LQR problem actually. So, if you standard LQR problem, then we know the solution for that, and the solution happens to be something like this: u equal to minus r inverse b transpose p into x, or minus k x, where p comes from this Riccati equation actually. Now, the only difference here is this Riccati equation is a function of state now, okay, and hence this you have to really see whether, I mean this p of it is not like a constant Riccati equation actually. In other words, every time when x changes, the equation itself changes, and hence every time we need to keep on solving this equation online actually. So, the procedure is like that: you somehow select a q of x and r of x, and write f of x as something like a x times x, and this is anyway ready, okay, this part. So, then you solve this Riccati equation and get a value for p of x. Once you have a p of x, then compute the control that way actually. Okay. So, as I told, the solution procedure demands that you have to solve this, keep on solving this Riccati equation every time, even though it is a finite time, even though it is an infinite time regulator problem actually. Remember, in infinite time LQR, we just need to solve this Riccati equation one time, and that can be done offline and all that. But here, if you have to solve this equation repeatedly, and it has to be solved online actually. And then you have to construct the controller exactly like using the formula for what you know for LQR actually. Okay. So, obviously certain implementation issues and all that. The first implementation issue is, okay, how do you solve this Riccati equation? That's what it boils down to, most of the difficulties, numerical problems actually. So, first thing is, you can think of solving the Riccati equation symbolically by longhand algebra, and if the problem dimension happens to be smaller, and we have given some examples before in this lecture series, it is possible to solve the Riccati equation symbolically. Okay. So, that is the best thing to happen if you can do that. The second best is, probably you can think of using some sort of a symbolic software package, something like Maple, Mathematica, MathCAD, lot of symbolic softwares are available nowadays, and you can solve this, try to solve this Riccati equation actually. If your problem dimension is not very high, then it will this software will try to probably give some solutions actually. So, this solution you use in this setting. So, that is next best actually. And if that too is not possible, then it is like a numerical solution sort of thing. So, you have to take a fast computer and try to solve this equation online actually. And remember, Riccati equation is now heavily studied. In other words, there are fast efficient algorithms also available. So, if you use that algorithms in fast high speed computers, then the online solution is still possible. Okay. If that too is not possible, then the last option is probably you take lot of points, okay, lot of different x and all that, and then try to get a solution for k, and then you have a set of k's, and hence you interpolate from there. That is the concept of gain scheduling actually. So, you can bring in the concept of gain scheduling, and then do this offline solution of this Riccati equation many places, and then schedule the gains actually, or interpolate the gains. So, these are the things that people suggest, I mean for using this SDRE online actually. Now, if we will see a nice example to show what is going on and things like that. This example I have taken from this one actually. It was a nice workshop, okay, in an American control conference in 1998 actually. Well, anyway, so this is a very standard benchmark problem. Okay, you have a quadratic you have a quadratic cost function and you have a nonlinear state equation. I remember I think you will be able to download this these PowerPoints as well. So, you can see this equation little clearly actually. Anyway, so this is x dot equal to x minus x cube plus u. Okay, so that is that's the standard benchmark example. We will also come back to this equation again and again in the dynamic programming lecture and all that. And in the dynamic programming lecture, we will actually derive the solution as something like this. Okay, in other words, this is actually this particular problem what you are looking at, even though it is a nonlinear problem, there is a exact closed form solution available for solving this actually. So, that gives us some sort of a benchmark control solution, and using this benchmark control solution, you will be able to demonstrate certain good things. In other words, if you are proposing a new method and you are getting a solution from there, then does it really give this solution or at least very close to this solution actually. Okay. And this also has another point, that means if you really think about another nonlinear control design method, the very thing that comes to mind is this so called dynamic inversion design or feedback linearization design actually. And those of you who are interested, they can see my other lecture on advanced control, where I have taken 1 or 2 lectures on feedback linearization, dynamic inversion design actually. So, what it happens is dynamic inversion is easy. In other words, you can just think about designing a controller such that the closed loop system will appear something like that actually. Okay. So, you have this x dot equal to, well, I can probably do that for you. Okay. So, we have this x dot equal to, okay, I think there is 1 second. X dot equal to x minus x cube, okay, plus u, that's the problem, and you want to operate with the x dot equal to minus x. This should be the closed loop. Okay, this is the system dynamic actually. Okay, so if you equate the two, then what happens here is you get this x minus x cube plus u is equal to minus x, because we know that this is a stabilizing solution actually. Okay, so this is stable, we know for sure actually. Okay. So, you solve for the control actually after that. So, it will turn out to be minus 2x plus x cube basically. It is very simple as that. It's very easily, in 1 line 2 line you can derive it, the control solution, which will make the system operate something like x dot equal to minus x actually, okay, which is stable anyway. Okay. That is what is done. Okay, so this is your feedback linearizing controller, which is x cube minus 2x, and then it operates like this actually. Well, you can also argue that this also does the job, because it also takes x to 0 anyway. That is what the asymptotic stability solution means. So, this kind of solution is probably too much complex and probably not needed basically. But we will quickly see that there are some nice properties of this compared to this feedback linearizing controller actually. That is what you can see when you plot it, the solution and things like that. It all happens that you can actually, first of all, you can put it into the this f of x is x minus x cube. So, you take it there and you just write it a of x equal to 1 minus x square into x. So, x minus x cube. Okay. So, this is something like this, x minus x cube is equal to x into, or this is something like 1 minus x square into x. So, this is your a of x actually. Okay. So, that is what is done here. Okay. Once you have that, you can put it back into the Riccati equation, and the Riccati equation will throw some equation like this, and hence you will get a solution for p, and then you get a controller which is minus p times x, because b is 1 here. So, it will turn out to be exactly same as what we have seen here actually. This, remember, this comes from Hedgehogy equation, Hamilton-Jacobi-Bellman theory. This can be derived that way, but if you just substitute this and then put it into the Riccati equation and then try to solve a controller, it happens to be exactly same actually. Anyway, so these are the two solutions available. One is the optimal control solution, the other one is the feedback linearizing solution or dynamic inversion solution. So, if you plot it, in a state space sort of thing, I mean, if this, what happens, this is actually control versus x actually. Okay. So, what you really want is some regulation about 0 point, this point actually. Okay. So, what happens here is you can see this that I mean both are fairly close to each other, okay, around the point, but as the deviation starts becoming more and more, then the feedback linearizing solution quickly diverges to infinity. That means, you really need a very high amount of control compared to the optimal control. In fact, optimal control just stabilizes to a finite value close to 0, and in fact, it goes to 0 actually when the deviation becomes large actually. Why does it happen? Because if you can see this is this system dynamics, x dot equal to x minus x q. So, the minus x q is actually a stabilizing term, okay, because if you take, okay, x dot equal to some minus x to the power k and k is odd, okay, then it can be very easily shown that okay, v of x you take this half x square Lyapunov function, and then v dot you can say x times x dot, and this is nothing but minus x to the power k plus 1, okay. I do not know. Okay. So, this is nothing but minus x to the power k plus 1 basically. So, which k plus 1 happens to be even, and hence it is always negative definite, and hence is stabilizing. So, in other words, what you see here this x to the power q minus x to the power q is a stabilizing term. However, when x goes to the magnitude of x is less than 1, then x cube is very less compared to x, and wherever you remember this is a plus power here, that means x dot equal to x, that is a destabilizing term actually. Okay. So, when the deviation is large, then minus x q is anyway stabilizing. So, we do not need any control, but when the deviation is small, it is an unstable system. So, we need a control actually for that, and all that good feature is there in the optimal controller. Whereas, feedback linearization or dynamic inversion based control, what it does is blindly applies this control. In other words, every time it tries to enforce this actually, this x dot equal to minus x solution. In the process, the control that is required also goes to infinity, because remember the plus x q term is there. When x goes more than 1, that means it becomes larger and larger, then it is a direct function of x q actually. So, the control magnitude goes to infinity actually. Yeah. So, that is a bad thing to have. So, when you have optimal control solution, there are certain nice things, nice properties around that actually. So, there is the authors try to rigorously point it out through this example, that you do not cancel beneficial nonlinearity by using this optimal control theory based approaches. Okay. So, this is called beneficial nonlinearity when you have minus x q term. Its power diminishes when magnitude comes down to below 1 actually. However, when the deviation is large, its power is good, and hence it should retain this feature as much as possible. The claim here is optimal control solution does retain that kind of behavior actually. Now, let us go through some little bit theoretical things, why it is popular and why there are nice behaviors and all that actually. First is some definition, and first thing is what is called as controllability and observability. Lot of you know, okay, but what you really need is just pointwise controllability actually. In other words, if you have these numbers for x actually, then the a of x and b of x is as good as some sort of a LTI system A and B sort of thing, linear time invariant, where constant A B are used actually. So, if that happens for every such pair, that A of x and B of x, you substitute some number, okay, and if the pair A B is stabilizable every point, then it is called pointwise controllable or pointwise stabilizable actually. Okay, for all x in the domain of interest omega basically. Similarly, A of x is an observable or detectable parameterization of the nonlinear system if this pair C of x and A of x, in this case you have to talk about an output also, and then output has to be written in this form. Okay. So, once you write it in this form, then it turns out that if the pair C of x and A of x are pointwise observable or detectable, then it is called an observable parameterization actually. Okay. So, if this happens to be A and B happens to be like pointwise controllable, then A of x is called controllable parameterization, and if C of x and A of x pair is detectable or observable, then A of x is called observable parameterization actually. And this concept is used for observer and filter design. We may not need it here because our focus is to design controller actually. So, the results tell something like this. Okay. It turns out that all these things we have mentioned, right, this I mean 5 conditions we mentioned here, and we also mentioned that this has to belong to class Ck actually, where k is at least 1. Now, this first theorem tells you, okay, first theorem tells us that in addition to those conditions, if A of x happens to be class Ck function also and is also both detectable and stabilizable parameterization, then SDRE approach always leads to a closed loop system that is locally asymptotically stable. Okay. So, remember this choice of doing this this f of x, writing this A of x into x is not unique. Okay. So, different A matrices pops up and things like that, and hence you have this pointwise stabilizability, detectability concepts and all. No matter what, I mean if you get whatever A of x, if it satisfies both the conditions, that means it has to be of class Ck and also it has to be detectable and stabilizable parameterization, then the nice theorem tells us that it leads to a closed loop system that is always asymptotically stable locally, of course actually. Okay. So, that local asymptotic stability guarantee is there basically. Okay. That enhances the confidence that okay, things will not go bad, no matter whatever A of x I select, I just have to verify that A of x is detectable, I mean and stabilizable, as well as it has smoothness properties actually. Okay. Okay. The second theorem tells us that for scalar problem, okay, like the example that we discussed here, this is actually a single state problem, that is there is a scalar problem. Okay. So, for scalar problem, the resulting SDRE nonlinear controller satisfies all the necessary conditions of optimality. That means, for scalar problem, it always leads to the optimal solution. Okay. It does not lead to suboptimality in scalar sense actually. And we have demonstrated that also here, because this example clearly shows that if you solve it through this approach, then you essentially end up with the same controller. Okay. No matter whether you solve from Hajjavi equation or you approach this through via Riccati equation, in other words via state dependent Riccati equation approach, and take this A of x equal to 1 minus x square and things like that, both will lead to the same solution actually. Alright. So, for scalar problems we do have a optimal solution actually. Okay. However, what happens to the vector problem? Okay. Now, the condition tells us that in general the vector problems, out of the 3 necessary conditions, the optimal control equation, that means del s by del u, is always satisfied. Remember, we have 3 equations satisfied: state, costate and optimal control equations. State equation is anyway satisfied because that is how the system dynamics will evolve, and then the remaining, out of the remaining 2, one equation is always satisfied. Okay. No matter whatever parameterization you do actually. Okay. So, the only problem is that the costate equation does not satisfy exactly actually. However, the costate equation, which is lambda dot is minus del s by del x, is satisfied asymptotically. Okay. And that happens only under certain additional mathematical conditions as well actually. Okay. And this is the reason for suboptimality of the controller in general basically. Now, the question is, what are those additional mathematical conditions and all? This tells us something like that actually. So, let B of 0 r be an arbitrarily large open ball centered at the origin with radius, some finite radius actually, okay, radius r less than infinity. Then assume that the functions, all these functions A of x, B of x, P of x, Q of x, R of x, and their gradients as well. That means, you take all these first order derivatives and all, they are all bounded, okay, within this ball. Okay. Understand that? So, it talks about some sort of an open ball, okay, centered at the origin with finite radius, and it also demands that all these functions along with their partial derivatives, they are bounded actually in that ball. Then it tells you that SDRE nonlinear regulation, in SDRE nonlinear regulation under the asymptotic stability, that means when x tends to 0, the necessary condition lambda dot minus del s by del x is asymptotically satisfied, and not only that, it is satisfied at a quadratic rate as well actually. Okay. So, to summarize in a simplistic thing, what happens is all that you have to make sure that all these state dependent functions as well as their partial derivative should remain bounded in that ball actually. Then this lambda dot equal minus by del s by del x, that is the Costate equation, is satisfied asymptotically, okay, and satisfied asymptotically at a quadratic rate, which is nice also. Very quickly it will converge to the the whatever lambda dot or whatever lambda pops up, that will quickly satisfy this as we start applying this controller and as x starts developing towards 0 actually. Alright, now coming to different thing, what are the capabilities of SDRE and all? This can be summarized something like this. You can directly specify and affect performance through the selection of appropriate state dependent state and control weighting matrices, that Q of x and R of x matrices actually. It can also, there are extensions to tell that it can also incorporate hard bounds on state and control actually, okay. So, that can also be accounted for actually. And it can directly handle unstable and or non-minimum phase systems also actually, okay. Now, that is a generic feature for any optimal control based design. So, it also retains that kind of behavior actually. And as we demonstrated in that scalar example, it can preserve beneficial nonlinearities as well actually. So, whenever the nonlinearity is good, it keeps it, whenever it is not good, it tries to kind of discard it actually. So, it can also be used for tracking control applications, okay. That you can see that in a couple of slides later. And it can be applied to a broad class of nonlinear system, that what we are talking is this control affine system and SDC parameterization, where A of x has certain nice properties. That is not a very restrictive class of nonlinear system, and many problems including aerospace problems as well as robotics and things like that can be actually modeled it that way, okay. So, the model naturally satisfies those kind of things actually. So, it is not a restrictive class of systems and hence it has been applied to many different class of problems, and hence it has gained its popularity actually. And interestingly, it also turns out that it can incorporate an extra degree of freedom in its design parameter to enhance the performance of the suboptimal controller, okay. We will see that in an example actually, okay. But what are the limitations? The very first limitation is it can be applied only to this class of nonlinear problems that you are talking about, which is in general true, but still we should remember that it is not a very universal nonlinear control design, okay, that you can blindly take and apply to any nonlinear problems actually. The second is obviously we have to live with suboptimality in general, and only when you have a scalar problem you have optimality, but in general you have to just get happy with the suboptimality of the controller. But the point here is, if you have this one, okay, it can incorporate some extra degree of freedom and things like that. I will outline that idea very soon. But with that, it turns out that the suboptimality of the controller that we are talking about is not really very bad. It can happen to be very close to optimal actually. Okay, and another limitation is it has this very major limitation rather in my view, is that it has this non-uniqueness of the parameterization of system dynamics. That means that the SDC form that we are talking about can be written in various ways, and that happens to be a major bottleneck actually. In other words, it works, but it will not work very good way, because it all depends on the choice or the experience or the insight of the problem that the designer has actually, okay. So, this happens to be kind of a drawback, okay, in this design, but no, the nice thing is, no matter whatever A of x we select, there is local asymptotic stability guarantee actually, provided that A of x satisfies some mild conditions actually. The other limitation is it is applicable to infinite time problems only, but well, I will not insist on that, because of late in another in 2010, 11 and all that, we have seen papers where the concepts like these are getting used for finite time Riccati equations also. So, it is not really a measured bottleneck, because ideas are start appearing for finite time problems as well actually. Well, remember, for finite time problems we need this differential Riccati equation, not algebraic Riccati equation actually, okay. So, anyway, those of you are interested can see some literatures around that line, but those theories are not as well developed or are not as straightforward as infinite time problems actually. Okay, so there are additional things to be done and all that actually. I encourage all of you who are interested to see, they can see some of this development in the literature actually. Another limitation is it demands the solution of a Riccard equation online, which may not be feasible for high dimensional problems. That means, if your Riccard equation, remember it is a matrix, a nonlinear matrix equation, and it has multiple solutions. We have to select a positive definite solution, things like that actually. So, when the dimension of the matrix increases, then we have this feasible condition, I mean online solution becomes an issue actually. So, how big the problem can be? Like if you have some 2 states, very much okay, 5 states, very much fine, 10 states, 20 states, 50 states, 1000 states and all, it's, I mean 50 states, no, I mean in other words 10, 20 states, okay, but 50 states you start worrying about, it all depends on the time constant of the process. But if you have a high dimensional problem, something like 1000 states, 2000 states, 50,000 states and all that, then obviously it is not possible actually. So, for flexible system dynamics and all, or infinite dimensional systems when truncated to some let us say 1000 states and all, then it is not possible to use the SDRE technique online actually. And also remember, there is no analytical guarantee of global stability. Okay. So, we also talked about stability, but the stability is local, it cannot be global actually. So, be careful about that aspect as well. Alright, so there are also some useful tricks suggested by Cottier and his group. So, first thing first, what if there is a constant bias term sort of thing? That means, remember what we really require, all this thing will revolve around this requirement that f of 0 has to be 0. Okay. If f of 0 is non-zero, then what do you do? Now, if it is non-zero, if you have x dot equal to f of x plus b of x plus some b vector, bias vector, let us say, then x dot will not go to 0. Okay, x dot will become b basically. Okay, then what happens there actually? Okay, so like that, many of these things will evolve around that actually. So, first thing is, if you have a bias term, then the one thing to handle it is to construct an artificial state, something like this, where alpha is very close to 0, a positive number which is very close to 0. Then what happens is it's like slowly decaying quantity sort of thing, but the decaying is such a slow rate that I mean for all practical purpose it's like a constant variable actually. Okay. Now, extending these ideas a little further, we have this suppose you have this cosine x form in the system dynamics. Now, we know that when x1 goes to 0, then cos 0 is 1, which is not 0. So, what do you do about that? You can do this manipulation, this cos x1 minus 1 divided by x1 into x1. Okay, if you see that, then when x1 goes to 0, then this 1 minus 1, which is 0, and you have this 0 by 0 form, and then you can talk, okay, it's a finite number sort of thing, it's not very bad that way. Then you have this plus 1, and this plus 1 can be interpreted as a bias term, and hence it can be handled this way actually. Okay. Then what happens for uncontrollable and unstable but bounded state dynamics? So, in those situations again you can introduce some term like this, minus x1 dot is that whatever existing thing is there, you just put minus alpha times x1 some term where alpha is again a small number. Then what happens, it tries to kind of nullify that when x1 goes larger and larger, even though alpha is small, x1 dot is largely dictated by this term, let us say. Then it tries to kind of prevent that from really becoming very large and all that actually. So, these are some of the tricks suggested in the literature to handle it within the SDRE framework actually. Now, coming to that concept that I was talking, that something called extra degree of freedom and all that. So, what happens here is, suppose because remember SDC formulation or SDC parameterization is not a unique parameterization. That means, somebody can come up with A1 and somebody else can come up with A2 parameterization actually. Now, the question here is, can I not formulate an A3 because I already know A1 and A2, something like this. This is something called convex combination of A1 and A2 basically. Okay. So, I construct an A3 of x, which is a convex combination of A1 and A2. Okay, that means alpha times A1 plus 1 minus alpha times A2, where alpha itself can be a function of x also. Then what happens that, okay, A3 will also work. Okay, how does it work? Now let's analyze this. If you substitute A3, that is A3 times x, and A3 times x is nothing but this one, because A3 is this one, right. So substitute A3 times x, and nothing but alpha x times A1 x of into x. This x comes here, and x comes here also. Okay. Then you can also see that A1 of x is a parameterization, that means this is f of x. A2 of x is also a parameterization, that is also f of x. That means the two terms cancel out and you have f of x only. So what you are talking is A3 can be a valid parameterization for the same f of x. Okay. In other words, if you know A1 and A2, then you can always construct an A3 something like this. What happens here is alpha becomes an additional tuning quantity. So it gives us some sort of additional freedom actually. Then this freedom, this alpha can be tuned through some sort of an optimization procedure offline. Now this alpha you need not fix it online, you can just do it somewhat offline, and then construct an A3 out of A1 and A2, and then operate your SDRE solution based on A3 parameterization rather actually. So that's the whole idea of extra degree of freedom and all that actually. Okay. Now before we move on, we will have another example. It's actually a two-dimensional example and all. We have this x1 dot and x2 dot something like this, and remember someone can construct A1 this way, okay, and someone can construct an A2 that way, okay. And if you construct an A1 somewhat like this out of these nonlinear equations and all, then the plots turns out to be something like this, okay. You can notice they are close, but in the initial phase, okay, if you notice here a little bit, initial phase these are not close actually, okay. They become very close to each other, okay, as time evolves actually. This is nothing but the time actually, okay. This is the time part, and this is your both state and control, okay. So you have your x1, you have your x2, and you have u actually. Anyway, so these are the control quantities and all. So the point here is even though to I it looks very close, but if you look at little bit carefully, then initially these are not close, but with time they become almost kind of overlapping actually. Similar thing happens for A2 also. Remember, A2 is a different parameterization for the same problem actually. So again, if you do the same exercise, and again if you try to plot it similar things, this is again T and this is both x1, x2 and u, then you can again see the similar behavior. In other words, initially they are not same, okay, initially there is some amount of error, and only later they become quite same actually. So what about selecting this way? You construct an A out of A1 and A2, just like an A3 sort of thing, but you can consider A, and then you operate it based on A, okay. So then you see that it is exactly same everywhere. Even this what you see is approximately same as the time goes to thing and all. It just you cannot distinguish anything really from beginning to end actually. That means it actually gives us some sort of a solution which is very close to optimal. Again, these are all T and all that actually. Okay. Okay, and you can also plot, okay, this okay. Now what has been done here, of course, is alpha is considered as a function of time, okay. In other words, alpha is fixed as we go along actually, okay. So that is what you see, that is some sort of a alpha trajectory or some sort of optimal alpha trajectory here actually, okay. And here is regular x1, x2 and u actually. So this, okay, if you do this, I mean if the procedure does allow that, in other words this tuning, alpha star tuning, is not very computationally expensive. In other words, you can do it in closed form and something like that. Then why not actually? You can do that online also, and you can also see that very quickly alpha star converges to some constant value and all that actually. Okay, so you operate, you keep on computing alpha star, and then you compute an A which is a function of that alpha, and then apply this A which is a newly constructed matrix, and I mean apply SDRE on A basically, okay, using A. Then this is what the result is, which is very neat to see actually. Okay. That demonstrate that this method or this design approach has additional degree of freedom, using which we can actually go very close to optimality actually. Alright, so that's all about SDRE control design. And more on that, I will suggest that you read from references that I pointed out in the beginning. There are many concepts, nice things, both on control as well as observer filter and all that actually. Now, very quickly I will give an overview of what is called as theta D control design, which is again an extension of SDRE control design. And sometime, I mean, this is the this part of it is actually developed by largely with Jinming and Balkrishnan actually, was his Min was his student, Balkrishnan student and all actually. Yeah. Anyway, I will show that. So, what happens here is the whole concept of theta D control design tries to address one issue of SDRE, that online solution of Riccati equation is problematic actually. In other words, if the dimension goes bigger and bigger, online solution of Riccati equation is a concern. You cannot really do that online actually. So, how do you kind of circumvent that? How do you kind of propose some different technique which will address roughly the same thing, same problem or similar problems, but will not have that difficulty actually. So, these are some of the references, largely Jinming and Balkrishnan and all. And actually, I mean, Balkrishnan happens to be my PhD guide also. So, we had a common paper as well, okay, with the extension of this approach to this distributed parameter systems and all that. So, that is a different concept altogether. But the regular method, you can for knowing these details of the method, I will recommend this one. This has lot of these theoretical results, demonstrative examples and things like that, which will clarify your ideas very well. Okay, and this has been applied to various practical problems, not necessarily only academic problems. So, you can see some missile autopilot design and some reusable launch vehicle design. I mean, and then we also have this extension to distributed parameter systems, things like that. So, it is fairly generic and it can be applied to a large class of problems actually. So, let us see what it talks about. First of all, it talks about a fairly same system dynamics. That means, you have this control affine system, okay, x dot is f of x plus b times u. And then the objective is again same. We have this infinite time controller and we want to minimize this quadratic looking cost function rather. And we know from HJV theory, and we will see that in HJV theory little later, that optimal control can be represented as u equal to minus r inverse b transpose lambda, but optimal lambda can be represented as del v by del x also, where v star is nothing but optimal cost actually. And this optimal cost satisfies this HJV equation, and in putting that in HJV equation, you can see that this v star what you are talking about has to satisfy this, where v star is the minimum cost actually. That means, if you walk along the minimum control that minimizes this cost and all that, then that is the v star that will result actually. Okay. So, solving this equation in a closed form is a challenge. It is in general it is not feasible. So, people want to see what alternative things can be done actually. Okay, again as I told, I will not give a very detailed elaborate explanation, but in a quick overview sense. First of all, what you need to do is write this cost function as q times some perturbation terms, as well as this state equation as something like f of x into x, what you have here as something like a constant matrix A naught plus this expansion actually. Okay. So, I think there is a small error there. This is not required probably. Okay. All right. So, what you are doing is perturbing the cost function a little bit and modifying the system dynamics a little bit as well actually. Then it turns out that if you take it there, if you take this HJV equation and substitute that, then instead of q you have to substitute this expansion actually, whatever q plus this expansion is there, and this turns out to be like that. Now, here is the trick. What is done here is del v by del x, which is nothing but lambda actually. So, del v by del x is expanded in terms of a power series on some additional variable theta. Okay. So, Ti happens to be a matrix where theta happens to be some sort of a scalar quantity and all that actually, which is it is like taking the motivation from the power series solution of HJV equation and all that actually. We will give an example little later when you go along, but the difference is now sometimes people take the V star as power series expansion and all. Instead of that, what is done is as the lambda or del V by del x, which is a vector, that is expanded as some sort of a matrix times some scalar times the state actually. Okay. So, once you write this, okay, and then you can substitute it back here, okay, this expression you can substitute back here, and then collect various powers of theta, okay, because that will give a series in terms of theta and power, theta square, theta cube like that. This will also give a power actually, okay. So, you do that and then collect various coefficients, coefficients of various powers of theta, okay, and it so happens that ultimately it will result in some sort of a Riccati equation in this form, okay, and it will result a bunch of Lyapunov equations rather instead of Riccati equation in terms of the series expansion actually, okay. Now, so good thing is this T0 is a function of A0 only, and remember A0 is a constant parameterization. That means this Riccati equation what you are talking can be solved offline really, okay. So, we are talking about one Riccati equation which can be solved offline, and a bunch of Lyapunov equation that needs to be solved online. And this series, as if even though theoretically it is infinite series and all that what you see here, in a lot of practical application all that it is needed is about 3-4 terms in that actually. Very quickly it kind of converges actually. So, what it points out is one Riccati equation offline solution and about 4-5 Lyapunov equation which requires online solution actually, okay. And then this D1s are also appearing here and all that way, okay. So, what the solution procedure tells is something like that. You solve one solution from here and get your T0 ready, okay. Now, if you solve that this one, but you need a D1 ready also, okay, and D1 can be constructed something like this actually, okay. Di ultimately is something like this. So, first you get T0, then D1, and once you have D1 you get T1, and from there you get to compute D2, and once you have D2 you can solve for T2 like that actually. This approach proceeds like that way, okay. Okay, finally, once you have the solutions ready, then this U can be represented as something like this, because you remember U equal nothing but R inverse minus R inverse B transpose lambda, which is this, and this is nothing but this series actually. So, you can substitute back and get the optimal control solution in closed form actually. Okay. So, there is a construction of DI and you can see the paper for details, but the DI can be solved something like this. And remember this it does not come naturally, but here the investigators have put some Ki and Li here, which is claimed as something like an additional tuning parameter actually, okay. So, it happens that okay, it will satisfy some this kind of relationship, and where epsilon I, if you take DI this way, then this equation will be satisfied, where epsilon I is in this form actually. The claim here is if you do not do that, then it requires large amount of control actually, and this you have to be careful to tune this Ki Li in such a way that control requirement will be smaller actually that way. However, obviously there are whenever there is additional tuning issues, there are also like scopes for improvement and all. So, if somebody is interested to see further investigate and then come up with a systematic procedure of adjusting this Ki and Li, that will be nice actually. Okay. So, this is what I told, this term is used to prove convergence of the series. It is also, it guarantees some semi global asymptotic stability and all. It reduces the initial control level, that is what I told you already, and it adjusts the system transient performance as well actually. However, remember this Ki and Li did not come from the series expansion and all, it was just thought about it later basically, okay. And once you have this additional tuning parameters, then these are the advantages, but also remember that right now as far as my knowledge is concerned, this happens to be just tuning parameter. In other words, somebody has to select these values in trial and error. So, if any of you can come up with some sort of a systematic procedure of adjusting this KLI, that will be nice actually. Okay. Now, well, there are, I mean, I am not telling that the systematic procedures are not available. They are, the investigators themselves have actually explored that, but there is again there is scope of improvement on top of that actually. Now, one way that the authors propose is something like that. Okay, ideally, on the optimal path Hamiltonian has to be 0. We know that, On optimal path, remember one of our basic earlier lectures, we told that in general on optimal path Hamiltonian is only a function, Hamiltonian is constant actually, that is what we have shown, if it is not an explicit function of time. And in addition to that, in the regulator problem, if it is a constant and finally it goes to 0, then it is 0 everywhere, okay. Because at s t goes to infinity, then all state and control both should go to 0, and in Hamiltonian which is in this form will all go to 0 actually, okay. So, having say, I mean this is a kind of effect actually, in other words on the entire optimal path Hamiltonian should remain 0. So, you try to fix an KI pair which will make sure that happens actually, okay. So, what it tells you is you select an initial value of KI something like a guess value basically. Then once you start running the control, then you can compute your H, and iteratively you have to change this pair to minimize H, okay, in the least square sense actually, okay. So, this procedure can be run offline to select appropriate value of KI, but again when you talk about offline running, remember actually it depends on your initial condition of the state also. So, you start with a state and do this and again start with different state, you may not converge there, and so you have to talk about a batch minimization sort of thing. In other words, take a lot of initial conditions and try to kind of run a tunnel of trajectories and then try to do some sort of a iterative change and all that actually. So, anyway, so that is the approach which already there, but again as I told, if somebody can think about a better approach, that will be even good actually, okay. And again before stopping, this is the standard same benchmark example problem where x minus x cube plus u we just discussed in SDRE framework also. Cost function is again similar, and we also know that there is a closed form solution for that, and there is a, we discussed about that, one of the feedback linearization solution can happen to be like this, and this ultimately it cancels the beneficial nonlinearity and it leads to this large control effort when deviation is large actually, where SDRE did not have it. Now, the question is, does theta d also gives us the same sort of result actually, and happens to be yes, because now you can decompose it very easily. You can talk about A0 is 1, is remember the A matrix in SDRE was 1 minus x square actually, that gives us A0 equal to 1, and then well I can put it that A1 actually rather, okay, A1 is minus x square and things like that actually, okay, and with q equal to 1 and r equal to 1 actually, okay. So, theta d solution turns out to be something like this, T naught turns out to be like this, T1 turns out to be like that, T2 turns out to be like that, and D1, D2 we can compute it something like this, and then finally you can see that the results are very close to each other actually, okay. That means the optimal control solution in closed form and theta d solution is not very bad actually in that sense. So, in summary, there is a small comparison thing that you can think about. One hand we have an SDRE method, the other hand we have a theta d method. Both are applicable for control affine systems only, don't forget that actually, and both lead to suboptimal solutions, okay. And it requires adjustment of the weighting matrix and this q of x, r of x actually, but this method it requires adjustment of the weighting matrices and as well as other design parameters as well, okay. But here if you once you adjust the weighting matrix, it is all Riccati equation solution, you do not have a control on that actually, okay. It is just a procedure that you have to follow, but here in addition to selecting that q of x and r of x, you have to select additional design parameters. That means how do you decompose into that series a naught, a1 and all that actually, even this ki, li and all that way. So, it gives us lot of design parameters. One way it is good because you can tune the design little better, but the other way it is also bad because too many design tuning parameters means designers get confused and it may lead to more suboptimality and things like that actually. So, it is not really very good if you have too many freedom actually that way. Okay. So, in SDRE method it meets the state dynamics in terms of state dependent coefficient form, and as I told both this also requires that. So, in that sense this is not an advantage actually, okay. But this SDRE method demands that you solve this Riccati equation online, whereas theta d method what it tells you, that is the major advantage here, it says it demands that you solve a set of Lyapunov equations online. Remember Lyapunov equations are linear equations actually, they are not nonlinear equations. So, it can be solved very quickly rather, okay. So, in general it requires a little bit higher computational time, whereas theta d method can be done in a lesser computational time actually. So, this is the thing as a summary chart, and probably those of you are interested more, you can read more literature and then get familiarize yourself actually. So, with that I think I will stop this lecture, and thanks a lot.